Today we're going to talk about colligative properties. Colligative properties are properties which are based on the number of solute particles or ions that are dissolved in a given amount of solvent. So colligative properties, in order to do any of the calculations that we're going to be doing with colligative properties, we will need to deal with a different type of concentration term, and that concentration term is molality. It's very similar to molarity. Remember, molarity was the number of moles of solute per liter of solution. Molality is the number of moles of solute per kilogram of solvent, and that's going to be an important difference. For instance, this first question asks how many grams of potassium nitrate must be dissolved in 550 grams of water to produce a 0.060 molal solution. So we've just established that molality is the number of moles of solute divided by the number of kilograms of solvent. And in other applications we've used, remember, we can replace moles with mass over molar mass of the solute per kilogram solvent. So in this example, it's already given us a molality of 0.060 moles per kilogram. It's asking us to find, in this case, the mass of the potassium nitrate. So we're going to use the mass over molar mass form. And if we add up 1 potassium, 1 nitrogen, and 3 oxygens, we get 101.11 grams per mole. Dividing that by kilograms of the solvent. Be careful, lots of times it's given to you in grams, so make sure you change that to kilograms of solvent. And when we solve for mass, we are going to find that this is going to be the 0.060 moles per kilogram times 0.55 kilograms times our 101.11 grams per mole. Looking at our units, we see that moles are going to cancel, kilograms are going to cancel, and we're going to be left with grams of our solute, and that value ends up as 3.3 grams of our potassium nitrate. So that's molality. And most of the time we'll be asked to find it, more simply just find molality, but we need to be able to manipulate that equation when it's necessary. So the first of the colligative properties we want to look at is the lowering of vapor pressure. Anytime that we put any kind of solute into a solvent, it's going to lower the tendency of that material, of that solvent, to evaporate. For nonpolar solutes, it's simply a matter of getting the solute particles at the surface of the liquid, and they're getting in the way. They're inhibiting evaporation. So if you can imagine in this situation, if we had just some extra solute molecules in here, those solute molecules, again, would simply get in the way of evaporation, and we wouldn't get it would lower that tendency for it to evaporate. That's for a nonpolar solute. Now, if you have a polar solute and you're in a situation where you have a polar solvent like water, then you're dealing with ion-dipole attraction. So in this case, with these positive, let's say we've got positive sodium in here along with the water molecules. Those sodium ions are going to not only get in the way of the evaporation, but they're also going to be attracting the water at the same time. So we've got kind of a double whammy thing going on. In both situations, you're going to lower that tendency to evaporate. That's the colligative property for vapor pressure. Now, Raoult's law says that the new pressure of a solvent, once you've put some solid in it, is going to be equal to the mole fraction of that solvent times its standard or normal pressure, vapor pressure, when it's pure. So keep in mind that when we're dealing with mole fraction, we're dealing with moles. Let's say we're dealing with moles fraction of some substance A. It's going to be the moles of A divided by the moles of A plus B plus whatever else is in that system. The most common mistake is to take moles of A divided by moles of B and call that mole fraction. It's partial over total. So we've got to have moles of A both on top and on bottom. So that's Raoult's law. Let's look at an example. Now, I gave you quite the example here. I wanted to kind of give one that had about as much as I could throw at you. It says nitroglycerin is used in the manufacture of dynamite and in the treatment of certain coronary problems. If you add 0.454 grams of the compound to 100 grams of benzene at 25 degrees Celsius, the vapor pressure of the solution is 94.85 millimeters of mercury. What is the molar mass of nitroglycerin? And it then gives you the vapor pressure of pure benzene at the same temperature is 95.00. So it's giving you a situation where it gives you a vapor pressure with something added to it, and then it gives you a vapor pressure. So remember, this is going to be P, and it gives you the vapor pressure of pure benzene. That's going to be our P0. So it gives us both of those values. So we're talking about the equation we just discussed, that P of the solvent, in this case benzene, is going to be equal to the mole fraction of the solvent times the pressure, the standard pressure of a solvent when it's pure. So that's our general equation. We know some of those values. We know that the pressure of the vapor pressure of benzene when it's got something dissolved in it, in this case nitroglycerin, is 94.85 millimeters of mercury. I'm going to start this a little further over because I'm afraid I'm going to run out of room. 94.85 millimeters of mercury. Now the mole fraction of the solvent is going to be the moles of benzene divided by the moles of nitro. And I'm just going to the nitroglycerin. I'm just going to abbreviate that nitro plus the moles of benzene. That's mole fraction, remember, for our solvent. And that's going to be multiplied times the vapor pressure of the solvent when it's pure, which they told us was 95.00 millimeters of mercury. So what about all these things I don't have values for? Well, first of all, if you'll notice up at the top, it tells us that we have 100 grams of benzene. So let's look at what that tells us. If we have 100 grams of benzene, remember that benzene is an organic compound. It's a formula that you really, truly need to memorize, because I really think now in the AP test they probably give us that formula because they're becoming bigger on the not memorizing so much. But C6H6, and if you look at this at the molar mass of C6H6, the molar mass is 78.12 grams per mole. And if we've got 100 grams of this, we're going to have 1.28 moles. So we know our moles of benzene, so we can substitute that in, and let's do that. We've got moles of benzene up here. 1.28 And we've got moles of benzene down here as well. Let's draw our lines in a little better. So right now, we've got everything filled in except for moles of nitro. It becomes just simply a math problem. So first of all, let's divide both sides by 95.00. And it's going to reduce to 1 on this side. We end up with 0.9984 is equal to 1.28 moles of benzene. I'm going to go ahead and write that as C6H6 over the moles of nitro plus 1.28 moles of benzene again on the bottom. Treating this as a single entity, I'm simply going to multiply both sides by this and divide both sides by the 0.9984. So, kind of a shortcut, which maybe the math teachers wouldn't appreciate. I'm just going to switch places with these. And so on the opposite side of the equations, I can do that and get moles nitro plus 1.28 moles of C6H6 is equal to 1.28 moles of C6H6 divided by 0.9984. Moles of nitro then. I'm working this out pretty straightforwardly and kind of breaking it down pretty good. We've got to get good at our mental math because they certainly expect us to be good whenever we're dealing with this on the AP test. When we divide these two, that becomes 1.282. So subtracting 1.28 from both sides, we get that the moles of nitro end up being 0.002 moles. That looks like a nice answer, but that's not what it asked for, remember. Remember that it asked for the fact that, it asked for molar mass. Molar mass, remember, is in grams per mole. It gives us one additional piece of information up in our problem. It tells us that we have 0.454 grams of the nitro. So if we know that, then we can solve, shot that up just a little bit too far, we can take the fact that moles of nitro are going to be equal to the 0.454 grams divided by the 0.002 moles, and we end up with 227 grams per mole for the molar mass of the nitro. Fairly involved problem. But like I said, I wanted to kind of throw everything at you so that you could see different ways that they could use this problem. So that was vapor pressure. Now, as far as the elevation of the boiling point, that's the next thing that's going to happen. The elevation of the boiling point is for the same rationale. It's going to take more energy to boil the solvent, make it reach the boiling point if there's a solute dissolved in it. To determine the boiling point of the solution, we use what I call the Kim equation. And this is the Kim equation, that the change in the boiling point is going to be equal to Kb. Now, Kb is a boiling point constant, and for every substance it's different. For water, this is the value for water, it's 0.512 degrees Celsius per mole. Changes for everything. The Van Hoff factor is how, I guess for lack of a better way of describing it, it's how many particles a substance would break down into if you dissolved it in solvent. Basically, if it's covalent, if it's a molecular compound, for a molecular compound, the Van 't Hoff factor um, is 1, not 0. The Van 't Hoff factor is 1. If it's ionic, we have to calculate it by determining how many particles, how many ions will be produced whenever we dissolve it in water. So for ionic, let's say we're dealing with NaCl. Well, if we dissolve NaCl in water, we're going to get 2 ions. The Van 't Hoff factor is going to equal 2. If we're dealing with FeCl3, dissolves completely in water, then our Van 't Hoff factor is going to be 4 because there's 1 iron ion and 3 chloride ions. Be careful. Let's say we have something like, let's just say Na2SO4. Maybe our tendency would be to say, okay, there's 2 sodiums and 1 sulfur and 4 oxygens, so evidently that has a Van 't Hoff factor of 7. No, it doesn't, because polyatomic ions count as 1. So in reality, we have 2 sodiums and 1 sulfate, so our Van 't Hoff factor is 3. And in general, for a molecular compound, they could give us all kinds of different molecular compounds we've never heard of. So if they give you a molecular compound that you cannot write a formula for, and you can't tell if it's got metal plus non-metal and it's ionic or not, then it's going to be molecular and its I value is going to be 1. So just remember that. So the question here is, what is the boiling point of a solution that contains 65 grams of NaCl and 800 grams of water? So the first thing we're going to do is to find our change in boiling point. So the change in boiling point is going to be equal to the boiling point constant times the Van 't Hoff factor times the molality of the solution. In this particular case, Kb is 0.512 degrees Celsius per mole. The Van 't Hoff factor for NaCl we've already established is 2. And for molality, remember molality is mass over molar mass over kilograms of solvent. It told us that we had 65 grams of the solvent. The molar mass of NaCl is 58.44 grams per mole. And it told us that we have 800 grams, or 0.800 kilograms of our solvent. So there's the setup. We get a boiling point change, a change in the boiling point of 1.42 degrees Celsius. Please don't stop there. People do that all the time. There's a boiling point change, but that is not the new boiling point of water. Think about it. That's almost the freezing point. So we can't forget to use this little equation here, that the new boiling point is going to be the normal boiling point plus the change, because remember, we're elevating the boiling point, we're raising the boiling point, so it's going to be added to 100. So the new boiling point will be 100 degrees plus the 1.42 degrees, or 101.42 degrees Celsius. So what if we're then dealing with freezing point? When we look at freezing point, it's the fact that when you put a solute into the solvent, it's going to spread apart the boiling point and the freezing point. It's going to make it higher in boiling point. It's going to make it lower in its freezing point. And the solvation, that whole process of dissolving, interferes with the crystal formation. It makes it harder for the solvent to form the crystals and to reach that, to get to that freezing point. So the equation is the same. The only difference is, instead of dealing with the boiling point, we're dealing with freezing point. And notice also that this says boiling point constant. It should say freezing point constant. The freezing point constant for water is 1.86 degrees Celsius per molal. And every substance is different. I is still the Van Hoff factor, and M the molality of the solution. So in the case, once we find that new freezing point, remember that you are lowering the freezing point. So you're going to take the normal freezing point minus the change. So in this case, it says, what is the freezing point of a solution that contains 123 grams of barium nitrate dissolved in 500 grams of water? So it's asking for freezing point, so we're going to use the fact that the freezing point change is going to be equal to the freezing point constant times the Van Hoff factor times the molality of the solution. Kf, we've said for water, was 1.86 degrees Celsius per molal. The Van Hoff factor, if it's barium nitrate, that's 1 barium and 2 nitrates, that's going to be a Van Hoff factor of 3. So Van Hoff factor of 3. And the molality then is going to be our mass of 123 grams divided by the molar mass of barium nitrate. And the molar mass of barium nitrate is 261.35 if you add it all up, grams per mole. We're going to divide that by the kilograms of solvent, so we need to change that 500 grams to 0.5 kilograms. And when we do, we get a freezing point change of 5.25 degrees Celsius. Remember that that's the change. In order to get the new freezing point, I didn't do that very well. Let's try that again. The new freezing point is going to be 0 degrees Celsius, the normal freezing point for water, minus the 5.25 degrees Celsius change, and we're going to get a new freezing point of negative 5.25 degrees Celsius. So, next example, let's do something that doesn't involve water. It says that we've got either camphor, which has a molecular weight of 152, or naphthalene, which has a molecular weight of 128 grams per mole. Either one of these can be used to make mothballs. We've got a 5.2 gram sample of mothballs, and it's dissolved in 100 grams of ethyl alcohol. The resulting solution had a boiling point of 78.90 degrees Celsius. Were the mothballs made of camphor or naphthalene? Pure ethyl alcohol has a boiling point of 78.41 degrees Celsius, and its Kb is 1.22 degrees Celsius per molal. So we know what the molar masses, the molecular weights of these two compounds are, so let's see what happens. We can calculate the molecular weight, the molar mass, of our substance using the chem equation, since we know how the temperature was changed, and knowing the Van Hoff factor, we can figure this out. So let's look at the boiling point. Delta TB is the boiling point constant times Van Hoff factor times the molality. And it said the boiling point changed from 78.90 to 78.41 degrees Celsius. So 78.90 minus 78.41, both of those in degrees Celsius, is going to equal 0.49 degrees Celsius for our change in boiling point, final minus initial. So there's our change in boiling point, and we know that the change in boiling point is going to be equal to the boiling point constant, and he gave us the boiling point constant as 1.22 degrees Celsius per molal. Remember, if we're dealing with a covalent compound, and both of these they're all nonmetals, so the Van Hoff factor is going to be 1. We know we're dealing with 5.2 grams of this substance. What we don't know is the molar mass. So divided by the molar mass, and we know that it's also in 100 milliliters of, 100 grams of the ethyl alcohol, so 0.100 kilograms of our solvent. And we're solving again for the molar mass. So we can take out this part, the 5.2 grams divided by the molar mass is going to be equal to 0.49 degrees Celsius times the 0.1 kilograms. We're going to multiply both sides by that. And we're going to divide by the 1.22 degrees Celsius per mole, and also divide by 1 here, but put the 1 down. It doesn't do anything. It doesn't change anything. So what that ends up with is that the molar mass is equal to, now remember, please be careful when you solve for this. Don't just take this and divide both sides by 5.2. That is done so often I can't even begin to tell you. And you'll end up with an incredibly small molar mass, the reciprocal of the molar mass. If you get a molar mass less than 1, you should know something's wrong, because there's nothing that has a molar mass less than 1. So not even hydrogen. So keep that in mind when you're doing this. If you get something less than 1, to readjust your thinking. So solving for molar mass, we would get 5.2 grams times 1.22 degrees Celsius per mole, and that's going to be divided by 0.49 degrees Celsius, and also divided by 0.100 kilograms, which will give us a value of 129 grams per mole. With that information, we look back at our original molecular weights, and we see that camphor was 152 grams per mole, whereas naphthalene was 128 grams per mole. Looks like this is naphthalene. So just a way that we can use this whole concept of colligative properties to determine molar mass. The last thing we want to talk about then is osmotic pressure. We elevate osmotic pressure, so that's our fourth colligative property, is the elevation of osmotic pressure. And we can, this is something we probably study more often in the biology area, but if we've got a semi-permeable membrane and we've got a solution on one side and pure solvent on the other, here's the solution, here's the pure solvent. That pure solvent is going to travel, it's going to move through the semi-permeable membrane in an effort to dilute that solution. And we can measure the force that does that with. The osmotic pressure would be a better term rather than force. But pi, which is osmotic pressure, is equal to the solution concentration. This time we're actually going to use it in moles per liter. Times R, the gas law constant, 0.0821 liter atmospheres per mole Kelvin, times the temperature in kelvins. So the question is, or the problem is, that beta-carotene is the most important of the A vitamins. Its molar mass can be determined by measuring the osmotic pressure generated by a given mass of carotene dissolved in the solid chloroform. Calculate the molar mass of carotene if 7.68 milligrams dissolved in 10 milliliters of chloroform give an osmotic pressure of 26.57 millimeters of mercury at 25 degrees Celsius. So the first thing we want to do, because this is an R-driven equation, is change that pressure and temperature. The 25 degrees Celsius is going to be 298 kelvins. And if we take the 26.57 millimeters of mercury and multiply it by the conversion factor of 760 millimeters of mercury per 1 atmosphere, we get a pressure in atmospheres of 0.0350 atmospheres. So So we'll get those changed first because we know that's got to happen. And now we know that our equation is going to be that pi is equal to molarity times R times T. We just determined that molarity was 0.0350, excuse me, not molarity, I'm sorry. The pressure was 0.0350 atmospheres. Molarity, remember, is mass over molar mass over liters, moles per liter. And we know the mass is 0.00768 grams. It told us it was 7.68 milligrams, but we need to change that to grams. Divided by the molar mass. And now it's divided by the liters. It said it was 10 milliliters, so that's going to be 0.010 liters. Times our R value, 0.0821 liter atmospheres per mole Kelvin, times our temperature of 298 kelvins. When we solve for molar mass, I'm not sure what, I've got an extra little thing here. Let's fix that a little bit. Divide that again by molar mass. There we go. That's a little bit better. When I solve for molar mass, I get this. Remember to make sure you solve correctly for molar mass and don't solve for the reciprocal. Molar mass is going to be equal to 0.00768 grams divided by the 0.0350 atmospheres times the 0.010 liters. And that's going to be multiplied by the 0.0821 volts, what I often call liter atmospheres per mole Kelvin for short, times the 298 kelvins, which gives us a molar mass then of 537 grams per mole. And those are the colligative properties.